Hey, physical science kids, Mr. Tima here. We're about ready to start part 4 of our electricity notes, and this is the final part of our electricity notes, and we're going to rock and roll it here and finish up. You should have just finished up the circuit construction kit and DC only. We're going to talk about those. We're going to use those kind of ideas today as we talk about what these things are actually called. Well, the first thing is called a series circuit, and a series just means in order. Okay, literally means it has to go in that order. Well, with a series circuit, the current can only travel in a single path, like a river. You can think of it like a river. Okay, I'm just going to open this up here so we can then talk about it. But as we go around the river, if you will, this this current has to jump each of these resistors, and it has to keep going in this order, and then it goes back to the start and it continues. There's one path, three sets of rapids on a river, and one path. Okay, if one of these breaks, that's it. It's over. The circuit's done. There's no more river. There's a big dam. You can't go down the river. There's only one path to that river. Okay? So here's a picture of it. Okay, you notice there's one path, there's one kind of motion around like this. Okay, you'll notice these are the resistors. Okay, these little paddles are the resistors, so they're kind of drawn up over here. Okay, we'll draw this guy over here. Here's our little pump, and remember it goes up, and we call that the potential because as it goes up, it has to use energy. And there it is. There we go, right there. That's what it looks like. That's our source, remember? Okay, and remember, as we talk about current as it flows around, just like it is here, we use the symbol for I for current, okay? All right, so that's a series circuit, one path. The water has one path to go around. Old Christmas lights used to be this way. If one of your Christmas lights blew, then the whole strand stopped, okay? And then again, just so you know, this is the drawing of this. This is almost the exact same drawing. This is what we call the schematical view, and this is the actual pictorial view. Okay, this is your source. Okay, this is your source. That would be what we plugged into the wall. And this right here is actually what we call a switch. Okay, that would be like the light switch on your wall. All right, so parallel. Now, parallel circuits are different than series circuits. They have multiple paths. Okay, I'm going to open this up right here so you can see that. If you notice, as we start out the river comes here, and it's like the river breaks into three spots. The river, you could either go down this rapid or you could come up here and go up to this rapid. You could come up here and go to this rapid. Okay, but at the end of the day, when you come out of whatever level you choose, if you will, they're going to join back together. Okay, they're going to come back out and then they're going to join back together. And at the end of the day, the current that started over here, the I that we started with, the river flow that we started with, is going to equal the river flow at the end. It's just that you may have taken a different path. Okay, it's kind of like those books when you were a kid where you got to choose what, like, you ever read those books and it was like, if you want to go down into the cave, choose page 68. If you want to go through the forest, choose page 39. It would take you like on a different adventure. Okay, but the difference between this is if one of these break, the whole thing doesn't shut down. It's like a ride. You come up here and you're like, I want to go this way. Well, this ride's closed, so I got to go this way, or I got to go all the way back here and go around. Either way, if one breaks here, they all don't break. Okay? So here's a parallel circuit. Again, if we look at the schematical view, here we come here. You have a choice. You're either going left or you're going right. Okay? You're going to go through the rapid or through the whatever you want to call it, the resistor, the adventure, and then when you come, you're going to come back together and we're going to leave the same way. And we're just going to keep going around the circuit like that. And you can kind of see that in the animation over here. All right, you have a choice. Okay, household circuits are a combination of parallel circuits. All right, we don't hook up our house in series. Now there's series within your house, like your bedroom might be a series where if you blow or use too much energy, all the power in your room goes out, but the whole house doesn't get out. And how does that happen? If too many devices are hooked up, the wires overheat, and we have safety measures in place. The first one is called a fuse. Now, we sometimes refer to it as the fuse box, but that's not really what you have. None of you probably have fuses in your house. A fuse was literally a tube. It looked like a cylinder, and inside this cylinder was a wire. And if it got too hot, that wire would melt and that would be the end of it. And you'd have to pull out this whole cylinder and you'd stick a whole new cylinder in. Okay. What most of you or all of you have now is what we call a breaker, a circuit breaker or a breaker box. That's like a panel in your house that has a bunch of switches in it. Okay. It has a bunch of these, like usually they're black and there's a switch. Okay. There's like a switch here. Okay. And what happens is inside this switch, there's a wire. And when it gets hot, it'll blow the breaker. You'll hear it go snap, and the switch will go to the other side. You go down there or unplug whatever you had to do, and then you go back and you flip the switch and it'll turn the power back on. So that's what a breaker box does. All right, complex circuits, just real quick, a complex circuit has both. If you look here, as it comes down, you have a choice. Whenever you have a choice, I could go left or I could go right. That's a parallel. I'm going to put a big P here. That's a parallel circuit. Looks like a D. We'll put a P there. That's a parallel circuit. But anytime you go down a path and then you have to go down the same path and hit another resistor, that's a series circuit. That's our S. So again, if you look right here, this part right here, this is the series part. But as you look as I could go this way or this way, that entire operation right there, that is a parallel circuit. So when you have both present, which is what usually happens, okay, that's called a complex circuit. All right, so here we go. We're going to do some rankings real quick, all right? We're going to do some rankings. All right, so you're actually going to pause the video here in a second. We're going to call this guy A. Oh, goodness gracious. We're going to call this guy B. Obviously, we're going to call this guy C, and we're going to call this guy D. Now, we're going to rank some things here first. First of all, we're going to go from high to low on all of these. Okay, we're going to rank them from high to low every time. And the first thing we want to rank high to low is we want to put the resistance, the omega, the resistance. I'm going to put R or, so resistance or omega. And remember, omega is how we say resistance. So I want you to pause the video and I want you to put these in order of the one with the highest resistance to the one with the lowest resistance. So go ahead and pause the video and do that right now. All right, well, welcome back. And here we go. The one with the highest resistance, and sometimes it's easier to say, well, this one has the highest resistance, which is B. And then sometimes it's easier to go, well, which one has the lowest resistance? And actually, the one with the lowest resistance is actually D. Okay? All right, so here we go. How did we do this? Well, it's actually pretty simple. Okay? So B, if you think about resistors as rapids or obstacles for a second, we say, well, look at this. B, you have to go, everybody has to go through two obstacles. D, you have a choice. You can either go through the left obstacle or the right one. So you actually have a choice. Okay, we'll come back to that. B, you have to go through one obstacle. Okay, or through two obstacles. Look at this one. Okay, look at this one. Look down at C. C is actually the next highest resistance. And then finally, A is the next highest and D is the lowest. I should have talked about that first. Sorry about that. So the next highest is right here because when you come here, you get to split. Okay, and when you split, you either go through two or you go through one. So if you think about it, instead of going through two, you might be lucky and get to go around one of them, but that would be the second highest resistance. The third highest is here because you have to go through this one every time. And then finally, D, even though you still only have to go through one each, you have a choice. And by having that choice, it actually speeds up how many gets to go through there. So that would be our highest resistance. So hopefully you took a guess on that. But now that you know this, hopefully this next part will be easier. So the next one I want to take a second is, which one of these has the highest voltage? Which one has the highest to lowest voltage? And remember, what is voltage? Voltage is the push. Voltage is the push, or how much energy is going to be needed, how much push we're going to need to do. So take a second and see if you can figure that out. All right, so voltage, the one with the highest voltage is actually, again, It's B. Guess what? It's actually the same thing. It's actually the same thing as resistance. And if you actually think about it for a second, if you have the highest resistance, or if it's the thickest pad that you have to fight through, then you're going to need the biggest push to get through that resistance. If it's the toughest river you've ever come down, then you're going to need the biggest push or the strongest people to get you down that, and so forth and so on. All right. So resistance and voltage are what we call directly proportional or directly related. If you have the biggest resistance, you're going to need the biggest push to get through that resistance. All right. And now I want to know which one has the highest to lowest current. And remember, what's current? Current is the flow. Okay. Current is the flow. So I'll write that. So take a second and guess which one has the highest to lowest flow. And remember, voltage is the push. So go ahead, take a second. We'll be right back. All right, welcome back. And some of you might have been able to figure out that it's actually going to be the opposite of what we just did. It's DA, CB. And the reason is, think about it conceptually. If I have the largest resistance, B, I have the largest resistance, which needs the largest push, then my flow will be the least. Because if I have the highest resistance, I'm going to have the least flow. If I have the lowest resistance, I'm going to have the highest flow. Okay? So hopefully you can see this. These are called directly related. These are indirectly related because they're opposites of each other. Okay? If you have the highest resistance, you have to push things through it the hardest. But if you have the highest resistance, you actually have the lowest flow of things. We'll talk about this. We'll walk through it. All right, to finish up, quick check. First thing is, I want you in your brain, if you were to draw on the screen, where is the source? This is the source. Very good. This is the source right here. Now, how is the current going to flow? How is the current going to flow? I'm sorry, which way is the current is going to flow this way? All right, the current is going to flow this way. Which way are the electrons going to flow? The electrons are going to flow this way because they come out of that negative side. All right. Where is the resistor? Right here. The resistor is right here. In this case, it's a light bulb. If we drew a resistor, we could draw a resistor like this with a little squiggly line. So just a quick check to see what you're doing. I'm going to finish up quickly here. What does this all mean for you? Well, it's all about this. It's all about saving some money. You've all seen the old school light bulbs. This would be like an Edison bulb with a wire in here. It had a little jagged wire that would heat up. We'd lose most of our energy to what? Heat. That's right. We lose most of our energy to heat. If you've ever had an old light bulb, you know they get like smoking hot. All right. And we lose some to actually producing the light, but we lose most of it to heat. One of these light bulbs right here, what we call the phosphorescent or the pigtail light bulb, one of these is equal to 9 of these. So the amount of energy that we use in 9 of these can be used in this exact same one for much lower energy costs. Again, it all goes back to Nikola Tesla. We're heating gas inside here. We're heating a wire inside here. So why is this all important? Well, think about it. What does this guy have? If we're heating gas versus wire, what are we doing? We have less what? What do we have here? Between a wire and gas, we have less resistance. Very good. We have less resistance, which means we're going to have a lower voltage needed. We're going to have a lower push needed. Well, a lower push means we have a higher current. We can put more current through here, but we don't need as much current through our house. Well, remember, the push and the current is what we pay for. If we don't need all that, we don't need as much of this coming into our house, which means we don't need as much money. We have less money. This guy right here has a really high resistance, which in essence means that you need to have a higher voltage, a higher push coming to your house, which means more energy or more current needs to flow into your house. And when you need this, that means that money is going to skyrocket. So that's what it all means. It all relates to how do we save money? All right. More current, more flow means more voltage push, which means more money you have to spend. Again, we're going to work on this. We're going to build some circuits by hand with some snap circuits and things like that. I know these notes were a little long, but until next time, Mr. Tima is out of here.